How are you, my learner? Welcome to our lesson today, that is Manifested e-learning platform. My name is Purity Anzelimo, and our subject of our lesson today is physics, and it's a continuation. We'll continue with the topic in Form 4, that is electromagnetic spectrum. That's our topic, electromagnetic spectrum. And in our lesson, during this lesson today, we'll look at numerical calculations involving energy. So we'll be looking at the numerical, or we'll be doing numerical calculations that is involving energy. And by the end of the lesson, you should be in a position to do calculations or get involved in calculation of energy, wavelength, frequency. That is what you should be in a position to by the end of the lesson. So generally or basically, we are going to look at the numerical calculations involving energy, the formula for calculating energy, and also other formulas will follow. Now, before we get to the numerical calculations, just a small recap of the previous lesson. We said that the properties of the electromagnetic waves, one of the properties among the 6 that we mentioned is that electromagnetic waves possess energy in different amounts. That's what we said, that the electromagnetic waves possess energy in different amounts. And something else that we said is that the electromagnetic waves are waves in nature. So they are transverse waves. They are waves in nature. And this way we are going to borrow when we now be calculating in this lesson. So we know that they possess energy in different amounts. They are also waves in nature. And therefore, to start with, I would like us to write the wave equation. Now that these electromagnetic waves are waves in nature, we are going to consider the wave equation. Wave equation derived in Waves 1, Book 2, whereby we say that the speed or the velocity, can first write it in ones. We know that the speed of a wave or the velocity is equal to wavelength multiplied by the frequency. And therefore, the speed where we use letter V, that is not the speed or simply the velocity, is simply equal to wavelength. The symbol for wavelength is lambda. And the symbol for frequency is small letter f. And therefore, V is equal to lambda f. And this is simply what we refer to as the wave equation, where V is the speed or the velocity of the wave. So V is the velocity or simply the speed of the wave. And the units for velocity is meters per second. Then our lambda, as we have seen, this is the wavelength of the wave, and the units are meters. And then we have frequency, which is in hertz. So that is the wave equation. And in this case, as we'll be talking about the electromagnetic waves, because we also say that one of the other properties of the EM waves is that they travel with the speed of light. So in this, we can now use C. Instead of V, we'll use C. Letter C represents the speed of light in a vacuum. So we are going to have it as C is equal to wavelength multiplied by the frequency, where we are saying C is simply the speed of light the speed of light in vacuum. So that is it. So this is the same wave equation that we are talking about, the wave equation, but in this case we are using C to represent the speed of light in vacuum. So in these calculations, we'll be taking the value of the speed or the velocity to be the speed of light. So even if you are not given in the question, you may not be given the speed, the value of C, or sometimes it can be V. You may not be given the values, but you should know that we say that all electromagnetic waves will travel with the speed of light, and therefore C will always be 3.0 times 10 power 8 meters per second. So this is our wave equation. That's the wave equation. Then I want us now to derive a formula for calculation of energy. So we are going to use these formulas together. The first one, the wave equation, and then the equation involving energy. As we said, electromagnetic waves possess energy in different amounts. And one thing I would like you to note is that energy is directly proportional to frequency. The more the frequency, or the higher the frequency, the more the energy. So we can say that energy represented by a capital letter E is directly proportional to frequency, represented using a small letter f. And therefore we can write it mathematically, whereby energy is directly proportional to frequency. That is what we have. E is directly proportional to F. So from the knowledge in mathematics, when we want to remove this sign of proportionality, we put an equal to sign and we introduce a constant. So we are going to have E is equal to a constant, which is represented using letter H, and then our frequency. And this H, which is our constant, is simply referred to as the Planck's constant. It is the Planck's constant. We have the Planck's constant, and it is approximately 6.63 times 10 power negative 34 joules second. You don't need to clamp this one. You'll always be given, whenever you are given a question involving you to use the Planck's constant, you'll be given that constant. At times, they also give us 6.64 times 10 power negative 34 joules second. So that is it. So we have energy, therefore, is equals to the Planck's constant multiplied by the frequency. So this is another formula that you need to note, where E is the energy, and energy is in joules. Those are the units for energy. So E is for energy in joules. H, we have seen, is the Planck's constant in joules second. And F from our area definition is the frequency in hertz. So this is another formula that we are also going to use, and we have seen we are getting it from energy is directly proportional to frequency. So when we were looking at the electromagnetic waves, therefore we can say, if I may ask you, which electromagnetic wave has the highest energy? Yes, it is the gamma rays, because gamma rays have the highest frequency, and the more the frequency, the more the energy. And of course now the radio waves will have the smallest energy because their frequency is the lowest. Then we can combine the two formulas and see what we have before we get into the calculations. So we have seen the first one is the wave equation, where C is equal to lambda F, and then we have seen energy is equals to Planck's constant multiplied by the frequency. Now, using this equation, we can make frequency the subject of the formula. So we are having E is equals to HF. So if we make F the subject of the formula, meaning that we divide both signs by H, we'll end up getting that our frequency is equal to E all over H. That is what we have. And therefore, we can come up with another formula where we have F, we substitute with E over H, meaning that the speed of light will therefore be equal to our wavelength multiplied by the frequency, which is E all over the Planck's constant. That's another formula. And finally, we can derive another one from this, whereby we are saying that our speed is equals to wavelength multiplied by frequency. We also have that energy is Planck's constant times frequency. Now, using the first equation, we can make frequency again the subject of the formula, whereby we have C equal to lambda F. So when we want to make F the subject, we can divide both signs by lambda. So we end up getting that frequency is the speed of light divided by the wavelength. So where we have F in our second equation, again we can substitute with C all over lambda. So we are going to have E is equals to Planck's constant multiplied by the speed of light divided by the wavelength. So provided you have the two formulas, these two formulas here, provided you have this one and this one, you can be able to get any other formula from the two. So from this, we can be able to get the wavelength of an electromagnetic wave, frequency. We can also be able to calculate the energy, and we can also be given all the others, and we are told to calculate the Planck's constant. So I want us to get into questions. So that is it. Those are the formulas that we are going to use. The wave formula, which is this one, and also the formula relating energy and frequency, which is E is equal to Planck's constant multiplied by the frequency. And always ensure when you are doing any calculations involving this, ensure that every quantity is in its SI unit. So if, for example, you are given frequency in megahertz, always ensure that you first convert into hertz. If you are given, for example, the wavelength in kilometers, always ensure that you convert it into meters. So you shouldn't be in a position, if you are given energy, for example, in kilojoules, convert it into joules. So calculations should be done when the quantities are in their respective SI units. So I want us to go back into a question and see whether we can be able to apply the formulas that we have been able to derive. So some examples. So example number 1, we have the following question. We have green light has a wavelength of 5 multiplied by 10 power -7 meters. That is the wavelength. You are told to calculate the energy it emits. Calculate the energy it emits. And you have been given the value of H to be 6.63 times 10 power -34 joules second. So that's one of the questions that you can be given, a very simple question here. Green light has a wavelength of 5 times 10 power -7 meters. Calculate the energy it emits. And the Planck's constant is given as 6.63 times 10 power -34 joules second. So whenever you are given a question in physics involving calculation, it is always good to first analyze, state what is given and then what is in question and see the formula that you need to apply. So here we have been given the wavelength. So wavelength we have as 5 times 10 power negative 7 meters. Then we also have the Planck's constant, which is 6.63 times 10 power negative 34 joules/second. Now, from this, what else do you think we have been given, though it may not be written here? What else do we know? Now, we are talking of green light. Green light is an electromagnetic wave because it is in that group of the visible light. And therefore, the speed of the green light is the speed of light. And therefore, we have C, which is 3.0 times 10 power 8 meters per second. So you may not be given the value here, but you know that green light is an electromagnetic wave, and electromagnetic waves travel at the speed of light, which is 3 times 10 power 8 meters per second. And therefore, we are told to calculate its energy. So we are calculating the energy. So we can come to the formulas that we have and see which one we are going to apply. So we have this energy, Planck's constant, we have the speed of light, and we have the wavelength. So we can apply that formula. Sorry, so we get the energy it will emit. So energy is equal to the Planck's constant multiplied by the speed of light divided by the wavelength. So that is what we have. So that formula has all the quantities that we have here. So our energy will therefore be Planck's constant, which is 6.63 times 10 power negative 34 joules/second, multiplied by the speed of light, which is 3.0 times 10 power 8 meters per second, divided by our wavelength. And our wavelength is 5 times 10 power negative 7 meters. So that is what we have in the question. And we want to be able now to calculate the energy. So we are going to find what we have in our calculators. You find what we have in the calculators. This is what we have. And you can see what is going to happen to the units so that we can get the units for energy. Because you can see here we have joules/second. We are multiplying by meters per second. Meters per second simply means it's like we are dividing. Therefore, meaning that this and this will cancel. So in the numerator, we remain with joules, meters. Then in the denominator, we have meters. Meters and meters will cancel. And therefore, our answer will be in joules. So you can feed it in your calculator and get the answer. So we have 6.63 multiplied by 10 raised to power negative 34. Then you are multiplying by 3 multiplied by 10 power 8. Then divide by 5 multiplied by 10. 5 multiplied by 10 power negative 7. So what do you end up getting as the final answer? You end up getting 3.978 multiplied by 10 raised to power negative 19. And as we have said, it is in joules. So that is what we have for that. That is the energy. We have said is Planck's constant multiplied by the speed of light divided by the wavelength. And you can see this and this will cancel. We remain with joules, meters, divided by meters, we remain with joules. And that is the SI unit of energy. Hopes that is clear. So we want to look at another example. So example 2. Question number 2. And remember, when you are feeding this in your calculator, it's always good that you remember to put the brackets. You just open the bracket, you write this, close it, you multiply, open it again, write this, you close it, you get the answer. You can write it first as the numerator, or you can just leave it in your calculator. Then you divide by, open the bracket again, 5 times 10 power negative 7, close it, and then the equal to sign. You'll be able to get 3.978 times 10 power negative 19 joules. So question number 2, or example number 2, a radio station is transmitting at a frequency, a radio station. So we have a radio station is transmitting at a frequency of 15.42 megahertz. So we are told to calculate the wavelength, of the transmission. Calculate the wavelength of the transmission. So that is what we have as our question. We are told that a radio station is transmitting at a frequency of 15.42 megahertz. Calculate the wavelength of the transmission. Calculate the wavelength of the transmission. So again, we analyze that question. What are we given and what is in question? So we have a frequency. The frequency given as 15.42 megahertz. Then what else are we given in the question? We have been given the frequency, but we know since these are radio station, it is transmitting radio waves. And radio waves are electromagnetic waves, and therefore they travel with the speed of light, which is 3.0 times 10 power 8 meters per second. So we want to calculate now the wavelength. So that is what is in question. Remember, before we calculate, we ensure that every quantity is in its SI unit. Here we have frequency in megahertz. We know that a million hertz make 1 megahertz. A million hertz, this is a million, is equivalent to 1 megahertz. So what about 15.42 megahertz? So we need to convert this in hertz, which is the SI unit of frequency. So we have a million multiplied by 15.42 divided by 1. So we have 15.42 multiplied by a million all over 1. So we end up getting this as 1542. So that will be 15,420,000 hertz. So that is the frequency that we are going to use. So we now come and look at the formulas that we derived. Which formula are we going to apply to get the wavelength? The formula that relates frequency, the speed, and the wavelength. And that is simply the wave equation. So we just come and note down the wave equation. The wave equation. And we say that wave equation C is equal to wavelength multiplied by frequency. So that's what we have. In our question, we want to get the wavelength. We can make it the subject of the formula, or simply we can just substitute what we have and finally get the wavelength. So we have our C as 3.0 times 10 power 8 meters per second is equal to wavelength, which is in question, multiplied by the frequency, and the frequency is 15,420,000 hertz. So that is what we have. These are hertz. So we want to get the value of lambda, which is the wavelength. So we have 3.0 times 10 power 8 being equal to, now when we multiply, we are going to have 15,420,000 multiplied by lambda. So it is 15,420,000 hertz. We want to get the value of lambda, not hertz only, but multiplied by lambda. So we want to get the value of lambda, and therefore we can divide both signs by 15,420,000 on both sides, 15,420,000. So of course this and this will be 1, so it cancels. So we remain with this. So our lambda will be 3 times 10 power 8 divided by 15,420,000. So again, you just pick your calculator and we feed this. So we have 3. Remember to put the bracket. You first open the bracket, put 3.0 times 10 power 8. Cross it, then divide by, open again, 15,420,000. Close the bracket and get an equal to sign, and we'll now be able to get the answer. We can give our answer correct to 2 decimal places. 2 decimal places. So you first get to 3 decimal places. We have 19.455. We can round off now to get to 2 decimal places, and we get that our lambda is 19.46 meters. Those are the units for wavelength. So our wavelength is 19.46 meters, and that is now the wavelength of the transmission for those radio waves. So we have 19.46 meters. Hopes it's clear. So once you are given a question, analyze it, get what is in question, and then using the formula, see which formula will apply. Like in this, we could not use the formula for energy, because this question is not asking anything to do with energy, neither are we given the energy. So analyze it, then get to know what is in question. So I would like us to do another example, example 3. Example 3. Question 3, we have the following. We have the following question. We are told that a radio is tuned into a radio station 144 kilometers away. 144 kilometers away. So the radio is 144 kilometers away from a radio station. So the first question is, how long does it take a signal to reach the receiver? So that's the first part of that question. A radio is tuned into a radio station 144 kilometers away. So here we are having a radio which is being tuned, and it is away from the radio station that is 144 kilometers away. So in this radio station, this is where the radio waves are produced. They are being transmitted, then they are received in the receiver, that's in the radio. So we are asked, how long does it take a signal to reach the receiver? So in this question, we have the distance. In this question, we have the distance that is covered by that radio wave, which is 144 kilometers. So we want to get the time it takes to get to the receiver. And we know that since this is a radio wave, again, so the speed of that radio wave will be the speed of light, which is, so we have the speed of light, which is 3.0 times 10 power 8 meters per second. So we want to know what's the time taken. So how long does it take a signal to reach the receiver? And we know from the knowledge in mathematics and also in physics, we know that speed is given by, speed is distance over time. So we have our speed, and this is not the speed of light, which is the speed of the radio wave. So we know that speed is equal to distance all over time. And our speed is 3.0 times 10 power 8 meters per second. Is equal to distance. Our distance is 144 kilometers. And we want to know the time that will be taken. And since here we have kilometers, here we have meters, we need to convert this distance in meters. So we convert the kilometers in meters. We know very well that 1,000 meters make 1 kilometer. So when we have 144 kilometers, simply multiplying by 1,000 to get 144,000 meters. So we have 3.0 times 10 power 8 meters per second is equal to 144,000 meters all over the time taken. So we want to get the value of time. So we have 3.0 times 10 power 8 meters per second equal to 144,000 meters all over time. So we come and cross multiply. So we are going to have 3.0 times 10 power 8 meters per second multiplied by time equal to 144,000 meters. So remember, we still want to get the value of t, which is the time taken, or want to know how long it takes the signal to reach the receiver. So we have 3.0 times 10 power 8 meters per second times time equal to 144,000 meters. So to make t the sum check, we divide both signs by 3.0 times 10 power 8 meters per second. This sign we have 3.0 times 10 power 8 meters per second. So of course this is going to cancel. Then now we can divide this using our calculators. So you just pick your calculator and divide. We have 144,000 divided by, sure you open the bracket, 3 times 10 power 8. So what do you end up getting? So we end up getting that our t, which is now the time, is 4.8 multiplied by 10 raised to power negative 4. This is time, and the meters is going to cancel. So we have seconds. Just a very short time, It takes a very short time. 4.8 times 10 power negative 4 seconds. That is for the signal to get to the receiver from a radio station which is 144 kilometers away. So that's what we have as the time that will be taken. So speed, distance over time, we have the speed, that is the speed of light because it is a radio wave which is an EM wave, and we have the distance in kilometers. We've converted into meters, which is the SI unit, and then we are able to get the time. So part B of that question, we have part B of the question. So we have answered the first part. So part B of the question, part B, we are told that if the signal has a frequency, of 980 kilohertz, how many wavelengths? Is the station away from your receiver or from the receiver? So in part B, we are told that if the signal has a frequency of 980 kilohertz, how many wavelengths is the station away from the receiver? So again, in this question, we've been given the frequency, which is 980 kilohertz. We've also been we have now been told to calculate the wavelength. How many wavelengths? So the wavelength is in question, but remember again, because it is a radio wave, the speed will be 3.0 times 10 power 8 meters per second. So that is what we have. We want to calculate the wavelength. We have the frequency and we have the speed. And we know that this frequency must be expressed in its SI unit, which is hertz. So we start by converting. We convert the kilohertz into hertz. 1,000 hertz make 1 kilohertz. So we have that 1,000. We can convert so that now we get the number of wavelengths. 1,000 hertz make 1 kilohertz. And here we have 980 kilohertz. So how many hertz are those? We cross multiply, we end up getting 980 multiplied by 1,000 over 1, which will simply be 980,000 hertz. So that's what we have. We have frequency, we want wavelength, we have the speed. So again here, as you can see, we apply the wave formula or the wave equation. And the wave equation is C is equal to wavelength multiplied by the frequency. Our C is 3.0 times 10 power 8 is equal to our wavelength, which is in question, multiplied by the frequency, which is 980,000 hertz. So again, we make wavelength the subject. So we have 3.0 times 10 power 8 equal to 980,000 multiplied by lambda. So to get lambda, we divide both sides by 980,000. 980,000. So this will cancel. So we end up getting our lambda, which is the number now of wavelengths, as we have the following as the wavelength. We can now divide using our calculator. 3.0 multiplied by 10 power 8. Then divided by, open the bracket, we have 980,000. So we end up getting the wavelength, or the number of wavelengths. We have the wavelengths as 306. We can write to 2 decimal places, 0.12 meters. So that is the wavelength. We have 306.12. 306.12 meters. So that is the wavelength. That's what we are asked in this question. Of course, we have been able to analyze. The time you analyze the question, you can see it clearly. So you'll be able to see which equation or which formula are you going to apply. So in this, it is very clear that we can apply the wave equation and we are able to get the value of wavelength as 306.12 meters. So that is it. I'd like to give you one question that you can try work it out. So you are given the following, an exercise for you here. So you are given the following. You are told that an X-ray machine produces radiation of wavelength 1.0 times 10 power negative 11 meters. An X-ray machine produces radiation of wavelength of 1.0 times 10 power negative 11 meters. Full stop. Calculate A, the frequency of the radiation. The frequency of the radiation. And number 2, its energy content. Number 2, its energy content. And in this question, you have been given the value of H, which is the Planck's constant, as 6.63 times 10 power negative 34 joules second. H is 6.63 times 10 power negative 34 joules second. So you should work that one out. And lastly, also calculate this. You've been given the following. Calculate, question number 2, calculate the wavelength of green light. Calculate the wavelength of green light of frequency. Calculate the wavelength of green light of frequency 5.0 times 10 power 14 hertz. Of frequency 5.0 times 10 power 14 hertz in air. Calculate the wavelength of green light of frequency 5.0 times 10 power 14 hertz in air. So you can do those calculations. And as we have seen, always remember the formulas. The two major formulas that we have been able to come up with. Number 1 is the one relating energy and frequency. And we have seen that energy is equal to Planck's constant multiplied by frequency. So note that. And number 2 is the wave equation. C is equal to lambda multiplied by the frequency. And when you have these two, you can now be able to calculate any quantity that you can be given. So that is it on calculations. Continue doing more and more to practice on the calculations involving energy and the wave equation. And therefore, since we have covered that, during the next lesson, we'll now be looking at now these electromagnetic waves. How are they produced? How are they detected? And what are their uses? Thank you for following.